This is engineering, mathematics 2. And my name is Doyol An. I'll put my email address just in case. 외국어는 맞죠? 그죠? 외국어는 맞죠? So the official language of this class is English. So everything I'm going to, give you in lecture will be in English, and all the exams will be also given in English. And I presume that you are also supposed to write your solutions in English too, because it's supposed to be an English class. And I think probably the most interesting topic for you today would be your grade. So my grade policy. Actually, I have only one grade policy. You will get A+ if you belong to top 10%. So this is the only policy. And the other grade is just up to me. And I think we are going to have about 2 or 3 quizzes. About 1 hour each. And one final. This is 3 hours. So about 60% of the grade will be from your quiz, and about 40% from final. So anybody can hear me well, especially in the back side? If you cannot hear me well, raise your hand. Okay, so that means my voice is loud and clear, right? What else? Maybe 1 or 2 surprise quiz. So instead of, I told you that I'm not checking your attendance. 출석집하네요. 대신 there is a surprise quiz. So surprise quiz is not announced before, and usually given on the lowest attendance class, and maybe 10 points each. So you can check this surprise quiz as usually other class will check the attendance. So 10 point or 20 point probably does not count much, because usually 500 points, 300 points. So the total of quiz will be around 500 points, and the final exam count about 300 points. So that's about 40%. So if you miss the two surprise quiz, that's only 20 points, right? So it's actually not much. But if you happen to be on the boundary between like A plus and A, or maybe A to B plus, so if your score is on the borderline between the class, between the grade, then the 20 points could change your grade. So I would advise you attend the class. But I don't care whether you attend the class or not. But so usually surprise quiz, we lock the door. When I announce the surprise quiz, and we just lock the door. So if you call your friend, that we are going to have a surprise quiz today, but maybe in 3 minutes he or she cannot come in because we are blocking them. So far, any questions about the policy of a grade? No question? Okay, I will make one exception for my class policy that I guess most of you may not be quite accustomed to speaking English. So if you have a question, you can actually raise your question in Korean in class. I mean, of course, you can ask any question in English, but if English is like on your bottom left, then you can ask a question in Korean. There's probably one exception in this class. So no more questions? Any other questions about the policy? So historically, more than, I think, half, or maybe around 60% will get B+. So probably don't have to worry too much about your grade, but etc., etc. I'll try to speak as slowly as possible, but if there is any topic or any things that you have trouble understanding in the class, probably it's the best way to ask a question. There's also one good way to stop the progress if you think if my class is going too fast. Okay, also one more thing. Usually when you take a quiz, I will let you prepare one cheating sheet. So you can prepare maybe 1 page A4 size, and then you can write down any formulas if you like. So actually you don't have to memorize the formula for my class. You can prepare 1 page cheating sheet. It's depending 1 hour for 1 page, 3 hours for 3 pages. So cheating sheet in Korean is cunning paper, right? So you're officially allowed to bring your cheating sheet. So usually I start with vector analysis for the second semester, but I changed my mind this morning, and then I'm going to start with the complex numbers. The first topic. As for the textbook, there is no textbook. I just teach whatever I like, and usually you can find my previous lecture note in 사이트가 어디지? Okay. So we also have one for previous class, right? 온라인 강의실에. Right. So the University of Seoul online lecture 강의실 will have the previous lecture note, and also I have all my class in the YouTube. David on engineering mathematics. Everybody knows about YouTube, right? So my ID is David on, and under the title Engineering Mathematics. I think I put since 2018, so about 5 years worth of class previous. All my classes in the YouTube. If you like, you can do 구독 and 좋아요. But it's just kidding, so don't worry about that. And after each class, I also upload my class. Like today's class, I'll just put on the YouTube tonight. So if you miss something, then it's a good chance to review. But unfortunately, my YouTube class will be like 2 hours or something, too long. Usually, I found that most of the YouTube things is like less than 15 minutes, right? But you have to be patient. It's going to be whole class, 2 hours. I don't edit. I just put everything into the YouTube. So complex numbers. Probably need to study the history of mathematics. And there is one very important thing, is 4 basic rules of arithmetic. One thing, you need to be familiar with my handwriting. Usually, my handwriting is not very, I'm afraid it's like just flying, right? So, but after maybe a few classes, you will get accustomed to my class. So 4 basic rules of arithmetics is, I think everybody knows about that since you're primary school. So 4 basic rules of arithmetics is Korean called 사칙연산. That include addition, right? 덧셈, and subtraction, 뺄셈, multiplication, 곱셈, division, 나눗셈, right? Addition, subtraction, multiplication, and division. So we are interested in 4 basic rules of arithmetic because if you like expand functions, for example, y, is it important? For example, if you have a Taylor series, 1 minus x plus x cubed 3 factorial, right? So this is what? Subtraction. This addition. X to the cube, x cross x, right? So this is multiplication. Finally, you have to have a division, right? So if you want to represent functions for any particular, like a number system, then that number system has to be close to the 4 base rules of arithmetic. That means the reason why the 4 rules of basic arithmetic, for basic rules of arithmetic is important is that if you want to represent a function, then you have to apply all those 4 rules, right? Multiplication, division, addition, subtraction. So we need a kind of number systems. That means we need a number system that is close to 2 for basic arithmetic operations. The important thing is close to 2. 닫혀 있다. Or you can define the new number using that particular 4 basic arithmetic operations within the same set. That means, in other words, if x and y belong to some set, and we do some operations, same set. So assuming the x and y are numbers that belong to a particular set S, and if you choose any number of member of that set S, and we do the arithmetic operations from that, and the results belong to that set, then you say that particular set is close to the 4 basic arithmetic operation. Then we say the set S is close to 4 basic arithmetic operations. So let's check the number systems we learned for the last 20 years of your life. So first number system you learn in kindergarten or elementary school is natural numbers, right? That is 1, 2, 3. And we are using base 10 numbers, simple, right? So we are let's just assume that we are using base 10 numbers. Anybody knows why we have been using base 10 numbers? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Because we have 5 fingers, right? So that's very simple. Historically, our ancestors used our fingers to count numbers. And so we have 5 fingers. Most of us, right? Somebody has 6 fingers, but that's an exception. So we have 5 fingers, so we have 10 fingers total. That's how we developed number systems based on 10, base 10. Assuming that 65 million years ago, a big atomic on the meteorite didn't hit the Earth. And somehow the dinosaurs survived and they become intelligent. What number system would they have been using? Simple question. So if, instead of us, if dinosaurs survived, because there was no hit of meteorite in 65 million years ago, and so teaching mathematics, and you are learning. We have notes. Taking notes. If dinosaurs survive, and if they're learning mathematics, what kind of number system will they use? Six? Okay, how many things to six? Raise your hand. Okay, how about 8? 10? Don't know. The rest? I think I would say 6. Because dinosaurs have 6 fingers, right? 3 fingers. So if they evolved into intelligent beings and they're learning mathematics, they'll be using numbers-based 6. So let's check if the natural numbers is close to which operations? 1 plus 2, 3 belongs to natural number, right? 2 plus 3, 6 natural numbers. How about 1 minus 2? It doesn't belong to natural numbers, right? Two divided by 3 doesn't belong to natural numbers, right? So we can see that the natural numbers are close to only multiplication and division. Addition and multiplication only. Let me just check the setting. Recording. Okay, camera resolution. Done. So that's your first grade. Maybe before present. So natural number system has been evolved as like exchange between caveman and the fisherman. So cavemen, they hunt rabbit. And fishermen, they hunt fish. So one day, the fisherman and huntsman met in the borderline and decided to exchange the fish and rabbit. Because huntsman was like getting bored of eating rabbit all the time and saying goes for the fisherman. So they set the exchange rate, like one rabbit for one fish. So they brought all the fishes and they brought the rabbit, and they have to count, right? What they do. They use your fingers, right? So what happens if you have more than 10 rabbits? What do you do? Bring your friend, right? Use his fingers to count. If it is more than 20, what do you do? Just bring one more person. So that's how they exchange the rabbit with the fish. And that's how the natural number system evolved. And I guess it maybe have been around probably more than 100,000 years since our very, very early ancestors started hunting and fishing. So natural number system is a very long history, but integer, oops. Integers usually they call z. That is natural number plus minus, right? So minus 1, minus 2, etc. plus and 0, 1, 2, etc., etc. So naturally, 2 plus 3 is 6, right? It belongs to integer. 2 plus minus 3 is minus 6, belongs to integer. 2 minus 3, integer. 2 also integer, right? So integer is close to addition, multiplication, and subtraction. How about division? 2 divided by 3 doesn't belong to, right? So integer is close to 2. Addition, subtraction, and multiplication. So historically, natural number system has been known to us for how long, do you think? I think probably 100,000 years. So when I'm going to enroll the class, there is going to be a blank page. I don't know how to get rid of this. Probably there's a way to edit this blank page, but integers has been only a few thousand years. And finally, we have rational numbers. Rational numbers is 유리수. The rational actually came to ratio, from the ratio. So Q is defined as M divided by N. And both M and N belong to integer. So rational numbers has been known around 3,000 years, around 10th century BC. There's a Chinese mathematics book called 주비산경. Treat the natural, the rational number systems. Probably that's the oldest mathematics book survived throughout history. Another book is 5th century BC, Euclid, the element. Also 5th century BC, Euclid wrote a very famous element that was the rational numbers. So 10th century to 5 BC is a very interesting period throughout the history. Can you relate why that particular era that the rational number system has been developed? 10th century BC, 5th century BC, historically. Anybody learn about the history in your Snoop? Tenth century BC to 5th century BC. There's one particular thing for that. It's related to ancient kingdom formation. 고대 국가 형성. Centralized government. The thing is centralized. Political power. So if you are king or if you are governor of some republic, what is probably the most important thing to manage your kingdom? Money, right? And where does money come from? Tax. Money from tax. And 10th century to 5th century BC, the basic industry was what? Farming. So how to divide the land is probably the most important thing. That's the reason why both the rational number system and geometry was developed in this particular era. So rational number and geometry were essential. taxation. So development of rational number system was not purely scientific, but mostly a political reason. How to tax the farmers, how to divide. The division is probably the most important thing at the time. That's the reason why the rational number system is developed. It's the first number system that is close to four basic arithmetic operations. So Q arithmetic operations. Oh. Probably can take a break for a few minutes and then continue. Around 2nd century BC, a Greek mathematician named Pythagoras asked one question: if there is a rational number Q such that Q squared is 2, so 2nd century BC, around maybe 200 years ago, the Pythagoras asked a very simple question. So by that time, the Greek mathematicians thought that the number system has been complete. It's complete. So they thought we know all the number systems needed to any kind of arithmetic operations or geometry. Then Pythagoras asked, okay, is there any rational numbers that gives, when you square it, gives 2? The answer is no, right? So Q is square root of 2. And he said, he defined the rational number plus irrational number is real number. So, for example, real number system. So rational number plus irrational number is called real number. So say x is a plus b root 2 belongs to R, right? And y c plus t square root of 2 belongs to R. Then let's check whether they actually belong to where A and B belongs to rational numbers. So Pythagoras thought whether this new number system is close to the 4 basic arithmetic operations. So let's say x plus y, a plus b square root of 2, c plus d square root of 2, a plus c, b plus d square root of 2, right? So definitely a plus c belongs to q, right? Because a and b are both rational numbers, and b plus d also belongs to q. So one thing is x plus y belongs to real number, right? And actually, I think probably you have done that in your middle school. You probably learned about square root or something in middle school, right? How about subtraction? X minus y, a plus b square root of 2, minus c plus d square root of 2, a minus c plus b minus d square root of 2, right? And it also belongs to real number because since a minus c belongs to rational numbers, b minus d also belongs to rational numbers. How about multiplication? X cross y, a plus b square root of 2, c plus d square root of 2 is ac plus bc square root of 2, ad square root of 2 plus bd 2. So it's ac plus 2bd plus bc plus ad square root of 2. So definitely it also belongs to real, right? Because ac plus 2bd belongs to q, right? And bc plus ad also belongs to q. So Pythagoras shows that at least real number system is close to addition, subtraction, and multiplication. How about division? X divided by. So this is important trick because we are going to show the same trick to show for that complex numbers. And how many of you have taken the spring class? Okay, so in the spring class, spring semester, I also showed some particular matrix, square matrix. It's close to 4 basic arithmetic, right? As long as the determinant is not zero. How about the division? C plus d square root of 2, a plus b square root of 2. So this is called nominator. In Korean, 분자, and denominator, 분모. So nominator is 분자, denominator is 분모, and it's called a fraction. 분수. Division, divide, division is an action, but the final form is called a fraction. Divide, division. Maybe they're too simple, but probably useful for your TOEIC exam, right? So in mathematics, there is one very simple but strong statement is that you can either add 0 or you can multiply by 1. That does not change the result. So you do not change the result by either add 0 or multiply by 1. It's a very important statement. Probably you need to memorize it. So when you do mathematics, simple calculation, you can either add 0, or multiply by 1 without changing anything. So let's apply that particular philosophy to this form. I multiply by c minus d square root of 2 and divide by the same thing. So this basically 1, right? I haven't changed anything. I just multiply the same. Divide the same thing and multiply by the same thing, right? So well, let's check the denominator first. C plus d root 2, c minus d square root of 2. Actually, you have done this many times in your middle school, maybe 7th grade. So c squared plus dc square root of 2 minus cd square root of 2 minus 2d squared, right? And they cancel each other. c squared minus 2d squared. Denominator a plus b square root of 2, c minus d square root of 2 is ac minus bd square root of 2 minus ad square root of 2 minus 2bd. So that is ac minus 2bd minus bd plus ad square root of 2. So it becomes this expression, c squared minus 2d squared, ac minus 2bd minus bd plus ad square root of 2. c squared minus 2d squared, ac minus 2bd minus c squared minus 2d squared, bd plus ad square root of 2. So it belongs to real number, right? Because the first term, because this belongs to Q, right? And this term also belongs to Q. So division is also real number. So real number system is close to 4 basic operations. So Pythagoras shows that the real number system was close to 4 basic operations, basic arithmetic operations. And it applies not only for square root of 2, but square root of 3, etc. And maybe include even pi and other numbers, which cannot be represented by the rational numbers. Anyway, so by the 2nd century BC, we have the real number systems, and your life would have been happy if that's the end of the story, right? I mean, you'll be really happy just playing with the real numbers, and everything will be just fine. Until 17th century, one crazy French mathematician asked the following question. His name was René Descartes. Descartes. Is there a real number? The same question as Pythagoras asked about 2,000 years ago. R such that R squared is minus 1. It's a very simple question, right? The Pythagoras asked Q squared is 2. So about 2,000 years ago, Pythagoras asked, is there any rational number system such that when it's squared, it gives not 2? So after almost 2,000 years later, Descartes asked a similar question: is there any real number system that gives, when it's squared, the result is minus 1? The answer: is there any real number that gives minus 1 when it's squared? No, right? Century. if you're Sherlock Holmes, then maybe you can take a look back at history and why Descartes asked that particular time. th century. Anybody can guess why at that particular time that question was raised? Perhaps because the character was a very rich man, he had nothing else to do, so he was really bored. So he asked the question, right? That's one possibility. But there may be some historical fact that this number system was necessary. It's actually 17th century. So Isaac Newton actually developed the mechanics, gravitation and calculus. So 17th century was like a booming era for physics and mathematics. And especially partial differential equations. 혐의분방 정식 has been very intensively studied, and some of the solutions actually made it the number system that gives -1 in the square. And sometimes it was necessary to consider the case when some R squared is -1. Especially when the solution, whether you want to ask the question whether the solution exists or not, especially with the existence of solution. With the question of the existence of the solution. And why partial differential equations become very intensively studied? 17th century was if you look back at the history, the era of great navigation, 대항해 시대. Then if you want to find some particular route or your position or whatever, such as type, then you need to partial differential equations. And whether you can find a solution or not, sometimes depending on the question of whether the particular number system gives minus when it's squared. So this is a very important topic. So maybe just summarize briefly why this number system has been raised in Korea. So 17세기는 여러분들 세계사 배웠어요? 수능 봤어요? 안 봤어요? 대항해 시대였어요. 그래서 뭐 새로 동인도 제도도 발견해야 되고 뭐 여러 가지 항로를 결정해야 되는데 그런 항로를 결정하기 위해서 필요한 것 중에 하나는 이제 어떤 특별한 지역의 두 속 간만의 차이를 찾는다거나 항로를 결정해야 되는데 그러려면은 뉴턴 역학에 필요한 여러 가지 복잡한 계산들을 해야 되는데 많은 경우에 편밀방정식을 풀어야 되는 거거든요. 근데 편밀방정식이 whether 솔루션이 존재하느냐 안 하는 문제가 중요해요. 왜냐면 솔루션이 존재 안 하는 문제를 열심히 풀어봐야 내가 원하는 항로를 붙여주니까. 그런데 그 솔루션이 존재하는지 안 하는지에 대한 그 문제 중에 하나는 제곱해서 마이너스 나오는지 안 나오는지. 여러분 한별식 별이 있죠. 어떤 2차 방정식 해가 존재하는지 안 하는지 할 때 B제곱 마이너스 4x가 이거보다 크다 작다죠. 그럼 그거가 그 제곱해서 뭐가 마이너스가 나오는 수가 나오고 있어요. 그래서 그런 문제 때문에 실수인데 제곱해서 마이너스 1이 나오는 수가 있는지 없는지를 아는 것이 굉장히 중요해요. 왜 우리가 서술을 이루어졌는지 알겠죠? 여러분 그냥 배웠을 텐데 이런 역사적인 사실을 좀 가능하면 actually doesn't change anything, but probably motivate you why we are learning these specific numbers. So the character actually 제가 한국말 한 건 잊어주세요. 그래서 수업평가할 때 쓰지 마세요. 한국말 했다는 말은. Just for your own benefit. So the character actually named this number as I. And he called imaginary number. In Korean, we call hosu, right? So imaginary number, it only exists in your image, in your brain. And Descartes was interested in whether this number system is also close to the four basic arithmetic operations. So I was hoping that why we are learning this particular number system from the historical perspective. So we call C. X and Y belongs to real number. So addition. So let's check whether C I hope you will get familiar with my handwriting. Even to my eye, it doesn't look very nice. Very clear. So C1 x1 plus I y1, C2 x2 plus I y2. So Z1 plus minus C2 x plus I y1 plus minus x2 plus I y2 x1 plus minus x2 plus I y1 plus minus y2, right? So it belongs to Z, no, not Z, C. So addition closed to addition and subtraction. How about multiplication? x1, x2 plus I, y1, x2 plus x1, I, y2 plus I, y1, I, y2. x1, x2, I, y1, x2 plus, assuming that we can interchange this I, x1, y2 plus I square y1, y2, this is minus 1, right? So x1, x2 minus y1, y2 plus I, y1, x2 plus x1, y2 belongs to C, right? So the complex number system is close to multiplication. Division Z1, Z2, x1 plus IY1, x2 plus IY2. I told you that you don't need to change the result by just multiply by 1, right? So you're same as so you can actually subtract x2 you can multiply by x2 minus IY2 and divide by the same thing, right? Without changing anything. So this is called denominator, right? Denominator. So let's check the denominator first. x2 plus IY2, x2 minus y2. x2 square plus I, y2 x2 minus I, x2 y2 plus I minus I, y2 square. And this to cancel each other, right? So, and this become plus 1. It's minus I square, right? So it becomes x2 square, y2 square. And especially, this is called complex conjugate. 컬레복소수? Raise a bell? Ring a bell to you? 공액복소수, 컬레복소수? In Korean, I think, complex conjugate 컬레. So actually, when I was in high school, it was called 공액복소수. It was defined, it was called, but sometimes later they have been changed the name into 컬레복소수. Denominator x1 minus iy1 x2 minus, oh no, this is plus y2 is x1, x2, y1, x2 minus ix1, y2 plus y1, y2 x1, x2 plus y1, y2 plus I y1, x2 minus x1, y2. So x2 제곱 스퀘어 y2 스퀘어 x1, x2 plus y1, y2 plus I x2 square y2 square y1 x2 minus x1 y2, right? So it belongs to complex conjugate, complex number system. So complex number systems is also close to 4 basic arithmetic operations. That means you can define complex functions, right? For basic arithmetic operations. That means we can define complex functions. So we are going to follow a bit more about Descartes' development. So Descartes was the first mathematician who introduced coordinate system. Cartesian coordinate. So we can actually define this complex number in terms of distance and angle. So R square root of x square plus y square, right? Theta, arctangent y over x. Then this is x, this is y. X can be defined as r cosine theta, right? And y is r sine theta. Then z is r cosine theta plus I sine theta. Assuming we have a Z1, another point Z2, so this is R1, this is R2, then Z1, R1, cosine, this is theta 1, this is theta 2, Z2, theta 2. Now when you multiply these two complex numbers, then we have a very interesting result. Z1, Z2, R1, R2, cosine theta 1 plus I sine theta 1, cosine theta 2 plus I sine theta 2, R1, R2, cosine theta 1, cosine theta 2 plus I square sine theta 1, sine theta 2 plus I sine theta 1, cosine theta 2, I cosine theta 1, sine theta 2. It becomes R1, R2, cosine theta 1, cosine theta 2 minus sine theta 1, sine theta 2 plus I sine theta 1, cosine theta 2, cosine theta 1, sine theta 2. Familiar? Probably you have learned that in your first year in high school. It's called 가법 정리, right? So this is actually cosine theta 1 plus theta 2, right? And this sine theta 1 plus sine theta 2. It's called addition theorem. 가법 정리. Familiar? Maybe in your 13th grade. In the first grade in high school. I was not sure. Was 수학의 정석 famous for your times too? 수학의 정석이 있었어요, 여러분 때? 없었어요? So this is actually one of the 필수 예제 문제. So it becomes R1, R2, cosine theta 1 plus theta 2, I sine theta 1 plus theta 2, so Z1, Z2, R1, R2, cosine theta 1 plus theta 2, I sine theta 1 plus theta 2. Let's consider the special case. R is equal to 1. So this is C, X, Y. This is 1. Theta. So if you square Z, what do you get? Cosine theta plus theta, 2 theta, right? C to the cube, this is called cube. 삼승은 큐브라고 그래요. cosine 3 theta plus I sine 3 theta. You can do blah 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 z to the n. Cosine n theta plus I sine n theta. So define some complex function f theta. Sorry. Sine theta, which is a complex formula. This is C, right? Then f theta to the n cosine n theta plus I sine n theta is actually f to the n theta. So we are looking for a function such that when you take nth power of x theta is fn theta. Actually, we know the functional form of this particular function. If you like nth power of some function is same as the argument is just multiplied by n times. You already know this function. It's simple. So anybody can guess what kind of function is this? Exponential function, right? So f theta maybe exponential alpha theta. So say f theta exponential alpha theta is same as cosine theta plus I sine theta, right? So if we expand the Taylor series, 1 plus alpha theta plus alpha square theta square, 3 factorial alpha cube theta cube, 1 minus x square over 2 factorial plus I to the theta minus 3 factorial over theta cube, etc. So from this we can say alpha is same as simply I, right? So we have a very famous formula called cosine theta plus I sine theta is exponential I theta. It's called Euler's formula. Euler's formula is really, really important. One thing is, I'm going to tell you later, but because of the Euler's formula, we have an electromagnetic wave propagating. We will come to later, but I'll just make a statement that this formula and also electromagnetic wave propagate because of Euler's formula. It's true. That means light exists. So Euler's formula is very, I think, profound. The meaning of the current universe, the space-time structure allows this Euler's formula is true. That is the reason why the light exists. According to the Bible, the first sentence in the Bible was, there was a light in the beginning, right? So 13th century Moses had a revelation about how the universe was created, and so the vision that the world started with the light. But with the Moses is Moses. Moses has some mathematics background. He might have wrote the Bible with there was a Euler formula in the beginning. Probably. But 13th century BC, they didn't have a complex number system at the time, right? Not even the real numbers. So Moses described the beginning of the universe as there was a light. So maybe you can take a break for a few minutes and then convene again, right? Okay, I will stop the third session a little bit early because you might be hungry, right? So after maybe a few minutes break, let's have class for maybe half an hour and then let's stop. Okay? 한 3분 쉬었다가 좀 일찍 끝낼게요. So we have derived Euler's formula. Exponential I theta is cosine theta plus I sine theta. What about the exponential minus I theta? Exponential I minus theta, right? So same as cosine theta minus theta, I sine minus theta. So cosine minus theta is same as cosine theta. But sine minus theta is minus sine theta. 1, 2. So 1 plus 2 gives exponential I theta plus exponential minus I theta is 2 cosine theta, right? So we can define cosine theta as exponential I theta plus exponential minus I theta divided by 2. 1 minus 2 exponential I theta minus exponential minus I theta is twice of I sine theta, right? So we can define sine theta as exponential I theta minus exponential minus I theta over 2I. You need to copy the screen first. Cosine theta and sine theta can be expressed as exponential something, Euler's formula. Okay, maybe. What about if we set theta I theta? That means cosine I theta is we use a definition. Exponential I theta over 2, exponential I theta, I theta, 2 over exponential minus theta, exponential theta. Familiar? Cosine hyperbolic theta, right? So cosine I theta is same as cosine hyperbolic theta. So we are defining complex functions. Same goes for sine I theta. Still you need to make a copy. Am I going too fast or it's okay? I guess I was hoping it's right. And cosine hyperbolic and sine hyperbolic functions are related to the imaginary of a cosine and sine functions. sine I theta is 2I exponential I theta minus exponential minus I theta 2I exponential minus theta minus exponential theta is 2I minus 1 times exponential theta minus exponential minus theta is I over minus 1 times twice of exponential theta minus theta. So actually you can multiply by I without changing anything, right? So this becomes minus I times sine hyperbolic theta. So we have cosine I theta is cosine hyperbolic theta. Sine I theta is I sine hyperbolic theta. So far we have derived very important formula from the Euler's formula that so we can actually define cosine z now. Say z using this property we can define cosine z. From the Euler's formula, we have this following formula, right? Ix minus y plus exponential minus ix plus y one over 2 exponential minus y. Exponential ix is cosine x plus I sine x plus exponential y cosine x minus I sine x. So we can combine them with the cosine x 2 over exponential y plus exponential minus y plus 2 over I sine x exponential minus y minus exponential y. So this is cosine x hyperbolic y minus I sine x sine hyperbolic y, right? On the other hand, let's check if the addition theorem also works. Same as the one before, that's right. So we can see that also works for the complex case. So cosine z, cosine x plus iy. If the addition theorem works, you can write this way. Cosine x, cosine iy, minus sine x, sine iy, right? Without parentheses. But cosine iy is same as cosine hyperbolic y. Cosine x, cosine hyperbolic y, minus I sine x. Sine iy is sine I sine hyperbolic y. So this result is actually same as also works. Then you can easily calculate the sine z using this addition theorem. Sine z sine x plus iy is supposed to be sine x cosine iy, right? Plus cosine x sine iy is sine x cosine hyperbolic y I cosine x sine hyperbolic y. You can also check this way. And if this, I will leave this as homework for you. So in my class, homework means you just work at home. You don't have to give it to me. You don't have to submit, just do it at home for your own benefit. Then you can define tangent z, right? Sine, cosine x, right? Tangent z is cosine z, sine z is cosine x cosine hyperbolic y minus I sine x sine hyperbolic y sine x cosine hyperbolic y minus plus, right? Plus I, let me see, cosine x sine hyperbolic y. But this is not very convenient because we have I in the denominator, right? So what do? We just don't do nothing, just multiply by 1, right? So do nothing. Means multiply by 1. So we can say cosine x, cosine hyperbolic y, minus I sine x, sine hyperbolic y, and we multiply by cosine x, hyperbolic y plus I sine x, hyperbolic y, and sine x, cosine hyperbolic y, plus I cosine x, sine hyperbolic y, multiplied by cosine x, cosine hyperbolic y, plus I sine x, sine hyperbolic y. Wow. So this is denominator. This is denominator. Denominator is easy, right? Seems like you are losing your interest because you passed lunchtime. Okay. Why don't I do this? Let's give us as a homework. You can work at home, but we will continue this next class. And we'll just stop here today, not tonight. What do you think? 집중력이 떨어지는 것 같으니까 여기까지 하고. 근데 이거는 집에서 한번 해보세요. 다음 주에 다시 할 테니까 한번 체크해 봅시다. Okay, so let's stop here today and